Now, assuming that you have had a go at this equation, in this particular case we would get that M equals 18498, putting in the temperature, the original temperature in centigrade, adding 273, so we're working in Kelvin, times log of 110, notice this is in hours, plus 18 gives us this as our answer. So then taking the other case of the lower temperature, 500 centigrade, plus 273 times the unlogged time, plus 18, and setting that equal to the same 18498, gives us TR equals 8.51 times 10 to the 5 hours. The remaining thing I want to say a little bit about is viscoelasticity. And again, this is extremely brief, but essentially this is the time-dependent response of loads due to flow. So it's similar to creep, but in a regime where actual flow is beginning to occur, seen commonly in polymers and in glasses near TG, i.e. near their glass transition temperature. Please note that at room temperature, silicate glasses are definitely elastic solids. They do not flow at room temperature. So if we apply a load in the sort of fashion shown here, so sudden instantaneous increasing load, hold that for a time, and then take the load back to zero, the actual strain response is seen like this. There'll be an instantaneous elastic response, then a flow based response, then when we remove the load there's an instantaneous elastic response, and then we start to see a flow based response. So essentially we don't reproduce the top hat that we see in the original loading due to these viscoelastic effects. Now polymers, the behaviour is strongly temperature dependent, and if we plot the log of the modulus versus temperature, what we find is that the modulus per temperature behaves in this sort of fashion shown here, and essentially the different regions correspond to different types of behaviour. Glassy, obviously modulus is relatively high, material behaves stiffly, and as we increase the temperature we first of all see a slow recovery on stress removal. Rubbery region we see a more rapid recovery on stress removal, then we get to a region where it's behaving like a viscous liquid. Overall the size of these regions will depend on the type of polymer that we're dealing with. Under constant strain, viscoelasticity will give rise to stress relaxation, so this can be characterized by relaxation time tau, which is the time taken for the stress to fall to 1 over E, i.e. 0.37 of its initial value. The stress equals the initial stress times the exponential minus the time divided by tau. So obviously if t equals tau, then we have the exponent of -1, i.e. we get 0.37. The relaxation modulus is given by the time-dependent stress divided by the constant strain that's been applied. Substituting in this equation we get sigma naught over epsilon naught exponent of minus t over tau, or we can say that that's then equal to E naught exponent of minus t over tau. So this is then our overall expression for the relaxation modulus, which is time dependent. You can also get viscoelastic creep, which is time-dependent deformation under constant load, and for polymers that can actually be very significant at room temperature. More crystalline polymers are generally more resistant to creep. So I've only really touched on the viscoelastic behaviour there. Really the primary part of this lecture has been on creep, which occurs at high homologous temperatures, generally homologous temperatures greater than 0.5. The creep mechanisms are often diffusional, and that included Kogel creep, which involves diffusion along grain boundaries, Nabarro-Hayron creep, which involves diffusion through the bulk material, and then Harper-Dawn creep, which is dislocation climb linked to diffusion. Then as you go to higher temperatures you get dislocation creep, which also involves an element of diffusion, enabling dislocations to get past obstructions, and finally you get dislocation glide, which is essentially conventional deformation. This is captured on a Wertmann-Ashby map, and we looked at 2 maps for tungsten and showed that essentially creep is reduced by having larger grain sizes. Looked very briefly at the Larson-Miller type approach to extrapolation and showed an example calculation, and finally also very briefly at viscoelastic behaviour. And that brings me to the end of both this session and the course. Thank you.